Good afternoon, everybody. Welcome. What is it? Second to last session today. My name is Michaël van der Haven, or Michael van der Haven for the English speakers. I'm a Dutch guy. My job is to talk a lot in a very opinionated manner as well, so that's probably why there may be an architect in the project that I'm working on. And in this presentation, I'm going to try to take you along on a well, more or less journey that I had in my own project, an architecture journey. That's also the reason why the KLM plane is there. The topic is Kappa, Lambda, and my journey, so KLM. And also the 747, because that has now become a legacy plane as well. We're going to miss that old bird. So, a bit of an outline. I'm going to tell you that it's not about airplanes, a little bit about the times that we're living in, the bias that we all have about legacy, because legacy is a very important component in any long project journey that you make. I'm going to highlight a little bit on the kind of stuff that we develop in the project that I'm working in. The legacy that we have to deal with in that project, how Lambda and Kappa-architectures are being applied there, and what the next new is going to look like without killing off the legacy, by the way. So I know in the opening speeches there were some evils about Hadoop and stuff like that. That's also something saying, well, avoid legacy at all costs. Well, sometimes you simply have to live with your legacy, and I hope that I can prove that you can do exciting, cool, new stuff, even with legacy. So, like I said, this is not about the KLM plane, but it is a good analogy on the journey that we've made in our project, the legacy that we have to deal with. But actually, I'm active in oil and gas. I'm active in what we call modeling and optimization, and that's where we build simulators. That's where we build how you model the subsurface and well space, how you model what kind of oil is captured, chemical properties, etc. But first, a little bit about the times, exciting times. I mean, I started out in 1997 as a semi-pro back then, and back then it was like, well, in-memory compute. Well, in one of the opening sessions, somebody said about a ZX Spectrum with 1 kilobyte. Well, in 97, I had a 486 machine with 64 megabytes of memory. Megabytes is not a typo, and I was king of the hill back then. Networking, that required pretty much nuts and bolts. I mean, we were still working with old, what is it? I even forgot the name, not the cat cables, but I mean, you literally had to screw on the network cable. And there was a big divide, of course. I mean, if you wanted to do something like distributed computing, MPI or something like that, if you want to do it as a home hobby project, well, you had to have a couple of very rich parents, or you had a very good job and a lot of free time to do that, because that was simply something you could not afford. So that was really for the big companies back then. But if you look at the 2005 until now, well, it's all internet, cloud services. You simply have to provide your credit card, and your credit card doesn't have to be a platinum version or something like that to have some, well, reasonable compute power available to you. Services that, yeah, you would have to be a top-notch programmer a couple of years ago, and now it's all available out of the box, like well, data lake services, advanced analytics is out there, machine learning. Follow a couple of online courses, and you can do at least something in that level. Are you a real specialist? Well, maybe not, but at least you know what you're working with. It's all open, cheap. Well, like I said, just present your credit card and you're up and running. And yeah, I mean, that makes these times exciting. But then again, if I again look back at 97, I mean, it was exciting to have a machine with 64 gigabytes or megabytes of memory. So I think all times are exciting, and I have had many moments where I thought, well, what's next? I mean, this is the ultimate, right? Well, I'm looking forward to having a new presentation in 10 years and see what's available then. The legacy bias. In my project, I have to deal with a lot of legacy, and I have to deal with a lot of bias on legacy as well, especially when we hire people and we tell about the systems that we're using. And we try to convince them that we're actually doing cool stuff, and we tell them that we have legacy systems in there of 10 years old. They're like, oh, well, this is the legacy perception that we have. I mean, it's like Stonehenge that you're looking, or what is it, the statues at Easter Isle. I mean, you're wondering, why is it there? Somebody built it, it's kind of heavy. Some people think it needs to be maintained. Well, it's good for tourists and stuff like that, but yeah, I don't really like it if people look at that manner at my software, but it is a bias that I have to deal with. But then again, yeah, you can still do cool stuff with legacy software by incorporating new stuff, and that's what I try to highlight along this story as well. So, like I said, it's old. Why did we ever build it? In a lot of cases, it's quite expensive as well. I mean, if I look at licenses for some of the legacy that I have to deal with, for every year, for every person, for every seat, I have to pay a license where you can buy a reasonable sports car as well. So it's kind of expensive, but then again, it's simply about, well, you have to live with it because your business owner is quite happy with it. Your business owner is also in the mode of, well, I spent a lot of dollars on it. In our case, we spent lots and lots and lots of dollars on it. Think 100 million and a multiple of that. But then again, we're taking business decisions with that software as well, and that's business decisions that are make and break on billions of dollars. So what is 100 million then? But yeah, we've spent that money, and if somebody says, well, hey, I've got this new hip technology, let's redo our software, my business owner is going to say, well, I already spent $100 million on it. Am I going to spend that again, or is it going to be a multifold of that? So, in a way, it's legacy software where you have to simply live with it, deal with it. I'm now going to go a little bit into what my team is building. Like I said at the start, we are working on modeling and optimization. And modeling and optimization is really about, well, somebody has done some kind of seismic interpretation. So we have a pretty good idea on, well, this is what's happening underground, and then we're going to make what we call structural models out of it. That's really capturing on, well, these are the compartments that we have underground, and this is how hydrocarbons are going to behave underground. And this is how the physics and chemistry is going to react when we start drilling a well and we introduce some kind of pressure difference. The thing is, this is a discipline that's actually a collection of disciplines. This modeling exercise where we say, well, this is what it looks like underground is what we call production geology. But the discipline that says, well, this is what it looks like when we start producing oil, that's called reservoir engineering. Then we have another discipline that says, well, I'm going to tell you about the chemical behavior underground. And another discipline is going to say something about, well, this is how you have to operate your service network that's on top of it. So we are easily, marrying 5 to 6 disciplines together that all have their legacy tools, tools that have been built for the, past 10 years. In some cases, with one of our tools, it's been around since 1968. So, and that's the kind of legacy that we have to work with. And there's a number of challenges around it. These disciplines are now used to working kind of separately from each other. they are expected to deliver a quarterly result on, well, this is the amount of oil that you're going to produce, or this is why you missed your target, and stuff like that. But typically, one engineer in one discipline is working on his modeling problem, and once he has created that modeling problem, he says, well, here's the data. And then the next engineer is going to pick it up. What we are trying to do is bringing those tools together, and instead of one engineer working for a week on a model or even a month on a model, is saying, well, you can work on it for a day, hand it over to a next engineer, and that engineer can work on it and give feedback on, well, this is what you missed, or this is the extra information that I need, etc. But the thing is, we are working with these legacy tools, and these legacy tools are really set up in a way of, well, if I need data, I'm going to slurp in this data, and I'm going to own that data. And once I'm done with the model, the next tool is going to slurp in that data, and it's very similar data. So for example, if we look at grid data, that's typical array data that is being copied over and over and over again. So we have a lot of duplication in data there. And now we start marrying these tools together, and we have engineers that are like, hey, this is a convenient way of working. And engineers that say, well, we have a problem called uncertainty modeling. I'll come back to uncertainty modeling a bit as well, but in uncertainty modeling, you have a couple of tools where you literally have a data explosion. But once you start marrying these tools together, and they all have this slurping mode, it means that they are starting to slurp all those extra copies or those uncertainty models as well. So we have a bit of a data challenge on that one as well. The tools are quite big. They're all around 1 million lines of code, 2 million lines of code. One project that I was involved in is running for 10 years now. And last week I ran a quick check on how many lines of code have we actually produced, have recycled. That's over 20 million lines of code, but the tool is only, 1.5 million lines of code in production. But I mean, there's a lot of effort in there. Another thing is, it's external vendors that we have to deal with. So we can also say to those vendors, hey, you're creating legacy software. It's not very nice if we have to work with it. And they're saying, yes, you're a very valued customer, but we have other customers as well. And if you want to have it changed, well, bring in a cartload of money, and we may think about it. So it's hard to convince them about changing their software. So our goals are really about, well, like I said, a typical engineer would create a file, hand it over to the next engineer, and that's all fine if you're working with one file, or if you're working with 2 files, maybe 10 files. But a typical asset is operating for 40 years, so you're producing thousands of files. So we have an army of workflow consultants that are telling engineers, thou shalt use this directory structure or else. And that's something we want to prevent. No more files. So anything an engineer is doing, I mean, underwater, we still have files, but we're never bothering the user with the file anymore. Data always has to be at your fingertips. So if you want to know something about what did the reservoir engineer do, and I'm a PG and I want to know what he did, I don't want to be bothered with going over to his desk, asking him to start up a tool for me or send me an email or something like that. Our platform simply has to be started up, and that data is always at your fingertips. You have view modes where you can say, well, now I want to be in an RE mode, now I want to be in a PG mode. Now I want to be in a physics mode. You get all that data. Our platform makes sure that that data is something we get from the right sources. You're not bothered with files anymore. And in the end, we want to do analytics on top of it as well. I mean, a lot of analytics is done in the tools, but we want to do holistic analytics across all the tools. And I said it before as well, we want to support modeling, what we call low fidelity modeling to high fidelity modeling. So instead of working on a very detailed model for a month and then handing it over to somebody else, we're saying, well, you can create a very coarse-grained model, handing it over, get results out of it. You have more information. You can start making a less coarse-grained or finer-grained model. And in the end, you have a high-fidelity model that you can work with. You could do that at higher speeds than simply handing over the data and hope that you did a good job there. I already mentioned about the slurping mode of the different tools. A model size is typically 50 gigabytes or something like that. So that means that in static modeling, we end up with a model of 50 gigabytes. In our dynamic modeling, we end up with the, dynamic copy of that model, also 50 gigabytes. Like I said, a real challenge is uncertainty, and that means, we do not really know what happens underground. If I say it's comparable to predicting the weather, but we know a lot less than the meteorologist does. It's a bit of that kind of work that we're working in, and that means that we have to make a few thousand variations of the model that we're working with. So that's 100 gigabytes times a few thousand. So we have a lot of data that we have to deal with. Traditionally, that was all limited to the simulator bit, but now we're incorporating it into the different tools, and we have to deal with the data explosion there. When we started out integrating those tools, we started out, like a typical developer. I have two tools, point to point, and it worked. And then I introduced a third tool, and then it became a bit more complex. Now we have, 6 tools incorporated with each other, and point to point is something that really does not work, especially if we do job scheduling. We do not really know what an endpoint is going to be. So that's where we started introducing a message bus. So all our data integration is now going over a Kafka queue, which makes it very simple because the producer simply knows one endpoint, that's the Kafka queue, produces its data there, and it's really up to the consumers to decide what they do with it. Another thing is that we have an architecture community in our customer that says, thou shalt use microservices as well. Like I said, these are legacy tools of 1 million lines of code, 2 million lines of code. That's not really a microservice, but we can make them behave like a microservice. And that's by simply wrapping them up in a container and operate in a containerized environment. And provide APIs for the subset of operations that those tools do. It has a bit of I think Fowler calls it a wrangling pattern. The only thing is that, yes, we are hiding away the complexity of the backend. But since it is an external vendor, we cannot really say to that vendor, hey, we now did something with fluid modeling, take out that fluid modeling out of that big simulator or something like that. So we do not really have that control, but at least our system looks like a set of microservices. This is a pretty much architecture picture of our current state of affairs. So we have Fusion, that's our app where we bring the user interface together. We have a couple of UI tools, the static modeling tool, dynamic UI, that is brought together in the Fusion context and provides a number of service APIs for the backends. You have a whole load of business services. Here I'm highlighting the static modeling app, the simulation engine that's running there, and underneath it there's a very big Kafka cluster where all our data is streaming. We have loads of consumers, so each component in the business services is a potential producer and consumer on the Kafka topics, and it also has provided us with a chance of, since we are letting all that data stream, We're connecting Spark, the ELK stack on top of it, TensorFlow on top of it, so we can do, well, the hip and trendy digitization stuff on it as well. And underneath, there is a set of legacy data APIs. We have introduced a couple of RESTful APIs as well, and all the data sources, or at least the databases that are being used by either the legacy tools or the databases that we use to store our integration data or the results data. But then again, I mean, this is the in-memory compute summit, and then I hear you asking, well, where is the memory part? Well, in essence, our Kafka cluster is really, at this moment, our in-memory bit. All the data that we're producing is being pushed onto the Kafka queues, onto the Kafka topics, and our extra in-memory bit is the Spark processing that we have in there. I started out, well, this is a Lambda and Kappa talk as well. If we look at Lambda architecture, well, there's typically 3 main layers or 3 main tiers or 3 main characteristics. Is, well, we have something that is really about speed. So our Kafka queue would be the speed part. Spark would be speed as well. We have a bit of batch processing. That's typically our job scheduling or the simulators that are running, and all the APIs that are serving the data, or in some cases also our tools that we're using to visualize the data as well. So if we take this picture again, the serving bits is the blue bits, so the user interfaces, the service APIs. The speed bit is the red bit, so Spark and Kafka. ELK is something where I'm a bit like, well, Elastic is that speed or just serving, and batch, that's really our app servers that are all running there. And I have grayed out the data tier here. But we're also introducing, or at least realizing, that we're introducing a Kappa architecture as well. Kappa is, in my humble opinion, just about processing and creating results directly on the data stream that you have. So if you have a topic where, say, that you have some kind of measurement coming in of a number of devices in a refinery, and you have some kind of trained model that says, well, if something happens with an air vent in this part of a valve, you have to do something with it. Move that data to a new topic because it requires new analysis. You create some kind of summary or something like that. Traditionally, you could say, well, that's the kind of data that I take off the queue. I start processing it in a batch-like manner. And when I'm happy with those results, I store it in my data storage. But now we say, well, we're actually going to push it directly onto the Kafka queue. Main reason is, like I said, our uncertainty model. In uncertainty modeling, the thing is that about 80% of the data that we produce is thrown away. A typical uncertainty model is where we have a model, we have a number of parameters in that model, and we start applying values to those models. So it could be a parameter like, I want to do something about a perforation height in a well. Perforation is about, well, we have a well bore in the ground, and it has a concrete casing. Well, concrete is nice stuff, it's very strong, but no oil or gas is going to flow through concrete. So what we do underground is that we perforate that concrete. But you have to know about, well, where is it that I'm going to perforate it? So you can think about perforation length, the size of the holes, the pattern that we're using for making those holes, because it has an impact on how safe the well is. And we have a pretty good idea about rock properties and permeability. And permeability is really about, well, how well does a hydrocarbon flow through the rock? But the thing is, it's always directional. And the thing we don't know is what direction is it actually going in. In a typical uncertainty run, we pick those parameters, we start punching in values, or these are the upper bounds or lower bounds, and we end up with loads of realizations there. In this simple example, I'm saying something like 25 values are, sorry, I'm a bit too far here. So parameter A has something like 10 values, parameter B has 250 values. This is the super simple example, and we end up with 2,500 rows in our uncertainty table. And that means 2,500 simulations are being conducted here. What a reservoir engineer does and what the PG does is he looks at the simulated production results. And based on those results, he's going to determine, well, this parameter has an influence, yes or no? And if a parameter has an influence, then he's going to decide, well, the value space that are provided to those parameters, this is the value space that is interesting. So we have all these nice Pareto plots, tornado plots, where we can say, well, this is the part that is interesting. And based on that, that's where we did our history match. Now we're going to do forecasting. So we're going to tell you how much oil or gas you're going to produce next year. But in practice, that means that you pick, what is it, 20% of the values that you entered. So if we have 25 values, or in this case 10% is only picked, so 25 values are marked as, well, these are valid values and these need to be explored further. It means that the rest of the data is thrown away. And in this example, it means that we have produced, what is it, a little over 150 terabytes of data, and 120 is going to be thrown away. And that's where a bit of Kappa kicks in as well, because we are producing all that data and we're pushing it onto a queue. And the nice thing about Kafka is, well, you set a retention period on your topics. So when we produce simulation results, we have a retention period of a day or a few days on those simulation results. And we know that we have sufficient processing power to determine within that day or within that few days, well, what data am I going to keep and what data am I going to discard? So any data that we have marked as, well, this is what we're going to keep, that's simply going to be a KSQL query or a Kafka Streams implementation where we say, well, this is the data we want to keep, and we're going to push that onto a topic that has a way longer retention period. For example, for a full quarter of a year, or even a full year, or in some cases 5 years or something like that. It really depends on legislation that we have there. So this is the area where we say, this is much more like Kappa architecture, because what we traditionally did is using that same pattern, or at least the pattern, that same workflow where we had separate software that was really looking at those topics and also determining, well, this is what we want to keep. But what we want to keep, or at least we first took all the data, plunged it into a Mongo database. Then we decide, well, this is what we want to keep and this is what we want to throw away, and then tell Mongo, well, 80% of the data that you have or 90% of the data that you have has to be deleted again. So we are introducing a lot of software components or mini services that do that for us. We implemented that, we have thrown it away, and we have replaced it with a couple of KSQL queries that do that job for us. So Kappa really has an advantage here. But we're at the in-memory compute. Ignite, I mean, it's a topic that has passed in many talks as well. Ignite is one of the in-memory solutions for simple data storage that we're looking at. It's really under evaluation, and Ignite is not the only candidate that we're looking at. But I want to highlight a little bit on why are we also looking at more in-memory database-like structures instead of only relying on the stream. Well, do quickly go back to this picture. One too many. In the data APIs, especially the one on the left, that is a data API that has been developed by one of our partners. And that is a data API that has been developed 10 years ago. And that is a data API, and I'm going to go back to the textual slide again. That's a data API that requires session state. 10 years ago, .NET developing C# was still all very hip. And it's also when we thought that Windows had the future. Not too proud of saying that. But, I mean, times are changing. And the way it is developed, it is something that only runs on Windows at this moment. And it is developed in .NET, really homegrown. And the result is that we have a state management or data state management solution that can run on only one node. And that was fine for that particular product, because that product was really set up as well. This is going to be something for a team effort where 5 or 6 people are working on it. And that's fine. I mean, that's all the state that we can manage on a single machine. If we have a machine with 64 gigabytes or 128 gigabytes, that's more than enough to accommodate that single team. But now we are, I mean, introducing this integrated pattern where this data tier is going to be hammered by our simulators as well. Since we are scaling out our simulator, I mean, in the example that I gave, it's 2,500 simulations that are running. On any given cluster that we have in our customer environment, we have over 200 jobs running every second. And we know in peak loads we have over 40,000 jobs running at the same time. So we are dealing with a cluster that would be hammering this solution with 40,000 connections that all need their state. Right now, we do not dare to go beyond the 100, but yeah, we see that the machine that is hosting it is cringing at the moment. And of course, we can always scale up to a machine with 500 gigabytes of memory or something like that. But what we would really like is that this session management is taken out and be replaced by an in-memory scalable database solution, and only the data where something is marked as well, this needs to be persisted, that it goes to, well, the cold storage on disk, and that the rest is kept hot in memory. It would allow us for horizontal scaling and things like that as well. Well, Ignite is something that we, at least one of my developers is looking at. Another developer is much more convinced that Redis is a better solution. Well, in this case, I'm happy to be the architect and say, well, I have a pretty much, what is it, hazy awareness of what you're doing. If you can produce me with the results, then we make a choice later on. Another vendor that we're dealing with is using SQL Server to more or less make a core dump of the state in their system. So one of the simulators is really about, well, time stepping, and after a few time steps, it dumps its arrays and state information into SQL Server. And the way it's doing that is by misusing SQL Server as a glorified binary backend. So any object or any class definition that we have has a representation as a table in SQL Server. We don't do anything with referential integrity there. I mean, we're only happy if an object can be stored. But in practice, I mean, it's fine if your simulation pauses for some reason and you want to restart it and that you take up that state from the database again. But in most cases, we're only interested in the values that a user has entered into the simulation and the results that we've produced. We're not interested in the state of the calculator. I mean, it's a calculator. I don't care that some kind of Jacobian has been running for, 200 iterations, 2,000 iterations, or stuff like that. When I'm done with the calculation, I want to get rid of that state data, and I only want to keep my predicted results. The vendor has recognized that as well, and they have a couple of customers that don't like it, that they have to buy SQL Server licenses or Oracle licenses for this purpose, because a typical simulator would only use files there. And they are also looking into, well, if it's only state data and it's not necessarily stored onto disk, why not use an in-memory backend? I mean, they could go the route of that other vendor and saying, well, we're going to do that by ourselves in memory, but they recognize, well, let's use something that's where many years more of experience is being utilized. A quick recap of our journey. Our journey was a typical journey where we knew that we wanted to have an integrated product, but we really didn't really know about the architecture that we were working on. I mean, we had a pretty good idea on, well, we need an integration database where all the integration or metadata is stored. We had a pretty good idea on, well, data needs to flow between the applications. But what the best pattern was to implement that's something that, well, we found out the hard way. And that's also, I mean, a bit driven by the way developers work. I mean, developers really love an RPC style of programming. I mean, if you tell them, well, you're going to go full asynchronous on a queuing system, well, I'd like to find that developer that is like, oh, that's in my CV, I have no problem handling that. Most of them are really about, yeah, an RPC-like endpoint. That's how we operate. And if you tell them, well, there is no endpoint anymore, only messages that pass by, it is a bit of a paradigm shift for them. It also had an architectural impact. Well, because it had a team impact, it had an architectural impact, then you start thinking about, well, okay, we recognize that something like an RPC pattern where we end up with point-to-point is not going to work. Let's try out a queue. First POCs with that queue were pretty much like, well, yeah, that's going to work. It does take a lot of refactoring, it does take a lot of rethinking, but it also means that you have to think about, well, what is it next that I'm going to do with it? And then at that moment, when we started to introduce that queue, we were thinking about, well, hey, this is going to be the backbone of our integration. And of course, once we had implemented that backbone, we still made the mistake. In hindsight, maybe it was a mistake. But we still started introducing all kinds of new services that were working on top of that stream, and really using that in a Lambda-like manner, which is fine to a point. But then we found out, well, Kappa is something that we can use to simplify it with. And I'm now saying it a bit in the wrong order. When we simplified it, then we realized, hey, we're doing Kappa. So in some cases, you're, inventing a wheel that other people have invented as well. And Lambda and Kappa is something that simply live together. I mean, we will always have to deal with simulators that need to do stuff in batch. And in all honesty, a lot of the machine learning that we're doing is batch as well. We will probably not get rid of that. So it's two paradigms, two architecture patterns that simply have to live together. And now my personal experience, well, they always say that that the young people can learn from the old people, and vice versa. Of course, I'm very happy that we have a team where we have very young people and where we have old-timers like me as well, and that we can get very well along on all these topics and really spar and think about it. So we really learn from each other. My personal learning, or at least something that I would like to promote, and what I try to promote here is as well, legacy is simply a given. Not everybody is working for a hip new startup where everything is built from the ground up and where you can follow the best patterns and practices. And in all honesty, I mean, if you're now working on a new pattern and practice and you're using some kind of technology that is now hip and great, and you start specializing in it, and you can say after 3 years, I'm a grid gain expert, maybe in 3 years you're completely outdated as well. So, and you've become legacy as well. So that legacy bit is something that is a given, and it's really about, well, how do you deal with it? But you also have to be open to new ideas as well. I mean, if you have invested heavily in knowing something and you've become a specialist in it, then it's very easy to say, if somebody else comes up with a new technology, and saying, yeah, well, I've been in this business for 5 years, 10 years, 20 years, and that's not going to work, and I know better. Always be open to new ideas, and well, we have shown that by being open to those new ideas, that we can actually do some pretty cool stuff. And yeah, well, I mentioned it before. We spend a lot of dollars on that legacy, and our business owners are quite happy that we can retain that legacy, and with a relatively low effort. They're happy with it, and in our integrated setup with using all these open source components and using tricks like containerizing everything, our deployment model has become a lot cheaper as well. So we're actually, well, we're making the workflows faster, but we're also making the hosting bit cheaper as well. So all in all, well, we have a happy business there. So. In that way, I'm proud and thankful of the team that has been building this. That leads me to the end of my talk.